varying temperatures and pressures and pH.
Okay, good afternoon everyone. As we know, methanogens are chemoautotropic anaerobic archaea that mostly consume carbon dioxide for their carbon source and hydrogen for their energy source and produce methane as an end product of metabolism. And we have been studying methanogens as ideal life form on Mars for a long time because they are anaerobe, they are not photosynthetic, they do not require organics. Also, they need carbon dioxide and hydrogen, and we know that carbon dioxide is abundant in Martian atmosphere. Also, hydrogen could be formed by serpentinization reactions. Interestingly, we have found methane on Mars. On Earth, we know that most of methane has a biological in origin. Therefore, methanogens are ideal candidates for life on Mars. Also, we know that the surface condition of Mars is extremely hostile to life because of low atmospheric surface pressure, low surface temperature, lack of liquid water, presence of oxidizing compound, and DNA damaging ultraviolet radiation. But the subsurface conditions are different. They are protected from radiation, which will have higher pressure, possibly higher temperature, and water might be present in liquid form. On Earth, we know that where there is water, there is life. Even we have found life several kilometers below the surface of Earth, and we are familiar with extremophiles. Based on their extreme conditions, they are classified into different groups such as thermophiles, barophiles, acidophiles, saccharophiles, and halophiles. So, similar to Earth, a subsurface biosphere could exist on Mars. This type of information inspired us to know the growth and survivability of methanogenic archaea after exposing them to different pressure, temperature, and low pH, simulating subsurface environment. And we also wanted to see their morphology due to the exposure to different pressure and temperature, and we also wanted to see the effect of temperature and pressure on their stable carbon isotope fractionation. So, we use Thermobacter wolffii that grows optimally at 55 degrees centigrade. They are obligate anaerobes and they use hydrogen and carbon dioxide and produce methane. We prepared 3 different sets. Set 1 was varying temperature, and we made growth media in bicarbonate buffer. Methanogens were inoculated in these media and incubated at 4 different temperatures: 45, 55, 65 and 75 degrees centigrade at atmospheric pressure. And we analyzed head space gaseous sample periodically. Second set was varying pH, in which we made media in bicarbonate buffer of different pH level 4, 5, 6 and 7. And again they were pressurized with hydrogen and incubated at their optimum growth temperature, which is 55 degrees centigrade, and head space gas sample were analyzed periodically. Third set was combined pressure and temperature, and we used 4 different pressures: 1, 400, 800 and 1200 atmospheric pressure. For temperature, we used 45, 55 and 65 degrees centigrade. This is the diagram of high hydrostatic pressure temperature chamber, in which we used a small high pressure cuvette and was placed from the top of the chamber, and a piston was used to pressurize the water, and the pressure was measured with pressure gauge, and to maintain the temperature of the system we use circulating water bath. So, this small high pressure cuvette was filled with methanogens in our anaerobic chamber and was placed in hydrostatic temperature chamber, pressure chamber for 15 hours. After exposure to desired temperature and pressure, we took images of some cells, and some cells were inoculated into fresh growth media, and again pressurized with hydrogen and incubated at optimum growth temperature, which is 55 at 1 atmospheric pressure, and head space gas sample was analyzed periodically. To measure methane concentration, we use gas chromatograph, and to measure stable carbon isotope fractionation, we used Picaro cavity ringed-on spectrometer. Now results. So at all different temperatures, even at 75 degrees centigrade, they produced methane. And second set was varying pH, and they produced methane at all different pH level. However, their lag phase increases with the decrease in the pH level. This is the graph of a combined pressure and temperature experiment. The top graph represents when they were at 45 degrees centigrade at different pressures, and the left side of the graph represents when they were at 55 degrees centigrade at different pressures, and this graph represents when they were at 65 degrees centigrade at different pressures. So in this graph, we see that they produce very high concentration of methane after they were brought back to normal pressure and their optimum growth temperature, which is 55. Then we calculated their growth rate, and we found that their growth rate did not change until 400 atmospheric pressure, but their growth rate increases with the increase in the pressure at 55 degree centigrade. This is the table of stable carbon isotope fractionation, and in this table we don't see any significant difference in their carbon isotopic data due to the effect of different pressure or different temperatures. We use this formula to calculate their carbon isotopic fractionation values. Actually, a stable carbon isotope fractionation is one of the methods that can distinguish between biogenic and abiogenic methane, and here we wanted to see effect of high pressure, high temperature on their carbon isotopic values. These are the images of Ulfii at 55 degrees centigrade, and this image was taken when they were at 1 atmospheric pressure, and this image was taken when they were at 1200 atmospheric pressure. At higher pressure, we found increased number of elongated cells, suggesting lack of cell division. In general, the growth and survivability of microorganisms depends on their ambient physical and chemical conditions such as pressure, temperature, and pH. And we know that extremophiles mostly belong to the domain Archaea because of they have unique membrane lipid bonding. Their cytoplasmic membrane contains ether bonds which are more resistant to heat. Also, some archaeal cytoplasmic membrane have tetraether lipids which forms monolayer which are almost impermeable to ions. And some archaea can produce pressure-induced proteins such as heat and cold shock protein, which help them to survive in extreme conditions. In our experiment, we have not investigated that which biomolecules are responsible for their survivability at high pressure, high temperature, and low pH. So we will investigate them later, but currently we are combining all three factors: pressure, temperature, and pH. We want to see their growth rate and survivability at these conditions. So in conclusion, we can say that Ulfii can tolerate pressure for 1200 atmospheric pressure, temperature up to 75 degrees centigrade, and low pH up to 4. And their growth rate increases with the increase in the pressure, and the temperature and pressure did not affect on their carbon isotopic data. And at high pressure, we found increased number of elongated cells, suggesting lack of cell division. And this work was supported by NASA Astrobiology Exobiology program. Thank you so much for listening.
Questions for Navita? All right.
Hi, great talk. Question is, Do you have any plans to get, I guess, in your model a little bit, or in your experimental work, a little bit closer to like near surface conditions on Mars? So like decreasing that pressure, decreasing that temperature, getting a little bit closer to what the surface conditions would be.
So near surface you're talking about, means temperature will be, what temperature are you expecting?
Well, I mean, I'm asking if you have any plans to get any closer or no? Okay.
Because my colleague C is working on low temperature and low pressure.
Oh, okay.
So C is working on that.
Okay.
So I won't be working on that.
Okay.
Hi, you might have gone over this too quickly and I missed it, but were you calculating growth rate by methane production in the head space, or did you do something like optical density?
No, head space methane gas sample.
Okay.
So not optical density.
Okay. Can you explain why?
How? Why?
Yeah, like why didn't you use something like optical density or?
Because our methanogens, it's very difficult to use optical density. It precipitates quickly. So we tried, but we did not get good data of OD. So we decided to use only methane concentration.
Okay, thank you.
Because media is also like very turbid and very initial OD is very high, so it doesn't work in our experiment.
Yeah, wonderful talk. I also work with methanogens, so yeah, methanogens. You changed many of the conditions. Are you also thinking about analyzing, or actually, what was the hydrogen concentration? Did you measure it, or
No.
no?
No.
Right. I mean,
we pressurized, so residual, we did not measure hydrogen concentration, just methane.
all right. Okay. Thanks.
Let's thank Navita again. We have to move on.